So we've just proved this very interesting theorem about matrix products and applying elementary row operations to them. But the real result that we're going to be interested in this section is a corollary to that main theorem. Now, corollary is like a little theorem that follows pretty much immediately from a bigger theorem. Okay? So this is going to be, now that we have that big theorem out of the way, this result is going to be pretty straightforward and easy to prove. So let B be an n by n matrix. Suppose we apply an elementary row operation to matrix B and we obtain a new matrix B prime. Then there exists another matrix E such that if we take the product of matrix E and our original matrix B, it's the same thing as B prime. I get the same result, which means that applying the elementary row operation to matrix B to get B prime is the same as multiplying by this particular matrix E. All right? So let's prove the result. Observe that B is equal to I sub NB. Okay, where of course I sub n is the n by n identity matrix. Okay, now what we're going to do is we're going to prove the theorem that we just proved above to this product. Then let E be the matrix obtained by applying the elementary row operation to our identity matrix. Okay? So we're just applying the same elementary row operation that we are going to apply to matrix B. We're going to apply it to the identity matrix. Then by the previous theorem, the theorem that we just proved, EB is equal to B prime. And we're done. Okay? All right, so maybe that requires a little bit more explanation. But that is the thrust of it. Okay, we have a product here, right? We have a product here, just like we do in the original theorem. Okay, in the original theorem, it was a general matrix A. In our corollary, we've swapped out A for the identity matrix. Okay? The original theorem said that if we apply a row operation to the product, that's the same as applying it to just the first matrix in the product and then taking the product. So I could, in other words, take the elementary row operation, apply it after I multiply matrices A and B, or I could apply it to just the matrix on the left and then multiply matrix B. Okay? Similar situation here. E is the matrix we get after applying elementary row operation to I sub n. Okay? In other words, if I sub n, that's like matrix A in our original theorem, E is like matrix A prime. And B is also the product of the matrices. So in this case, B and C are the same thing. Okay? So what this is saying, B prime is like C prime, and EB, E is like A prime. So I get A prime B equals C prime, which is exactly the result that we proved in our original theorem. Okay, so it really is just the same thing. I'm just doing some substitution. All right. So this matrix E here, we get it by just applying an elementary row operation to the identity matrix. This is, in fact, what an elementary matrix is. An elementary matrix is a square matrix formed by applying a single elementary row operation to the identity matrix. Okay, so now we know how to find one of these elementary matrices. Okay, we just take an identity matrix and apply the elementary row operation we are looking for. That gives us an elementary matrix. And if we have an elementary matrix E, and we apply it to a matrix, that is equivalent to applying an elementary row operation. So now instead of having to think more abstractly about these elementary row operations, we can think of applying elementary row operations as a matrix product. And that makes it easier to manipulate and think about applying elementary row operations.